All right, so all of these are useful rules that we're going to try to apply to the examples today. So for our examples today, we're going to use the law of exponents to rewrite and simplify the expression. First rational expression that's given to us. Take a to the fifth, b to the second, times a quantity of 3a squared, all of which is cubed. Put that over a to the ninth. We'll start off with one here that's got a lot of these rules applied. All right, how you might approach this. A lot of ways we could do this. But how we might start off. Maybe you want to clean up this numerator. And we see in this numerator that we got some parentheses. We're used to, usually when we simplify, getting rid of those parentheses. So let's start with the whole power to power rule idea. I'd have a to the fifth, I'd have b to the second, since the parentheses don't impact those. But then, since it's 3 times a squared, I would take 3, I would cube that. Right, I'd apply this power of 3 to that 3. I'd also apply this power to this power here on the a squared. So it'd be a to the power rule says multiply, so it's a to the sixth. All over a to the ninth. So trying to take this piece by piece, that helps us to get rid of the parentheses, right? If we continue to simplify the numerator, we could start multiplying some things together. We could also evaluate this 3 cubed. 3 cubed is 27, so I'm going to bump that to the front. b to the second is what it is. But with the a's, now we've got a to the fifth times a to the sixth. If you got like bases, you add your exponents here, so that would be a to the 11th. All over a to the ninth. The numerator is as simplified as we're going to get it because we're down to one variable of each type. We're ready to divide things out. The only thing we can really divide here are these a's, and when we divide with like bases, we're subtracting those exponents, so we'd have 27. If I try to go in alphabetical order here, it'd be a to the, subtracting those exponents, the second, and then b to the second. You're down to one variable of each type. You know you've got it simplified now. All right, if we're given another rational expression, let's take x to the negative 7th times b to the 5th in the numerator, denominator x to the negative 10th. Let's reintroduce what we know about all this negative exponent stuff. There's a couple of ways to do this one. One way, though, is if you want to get rid of the negative exponents to start, anytime you've got these negative exponents within this fraction as it's written, if you want to create positive powers, just change their locations. This x to the negative 7th, I could bump down here and make that an x to the 7th. This x to the negative 10th, I could bump up here and make that x to the 10th. A very quick, convenient way to change over the powers. So if I do that, I've got x to the 10th, b to the 5th now on top, and I've got x to the 7th on the bottom. You simplify at this point, basically carrying over the same rules as we did on the previous problem. You've got your x's as your like bases. So dividing that out, we're going to subtract the exponents. You'd have x to the 3rd, subtracting 10 and 7, times b to the 5th, or b to the 5th times x to the 3rd. That's one way to do it. Another way to do this problem, though, is if you notice you have like bases and we're dividing, and the negative exponents really aren't freaking you out all that much, what you could do is say, all right, with these x's, highest power of x is up here, right? negative 7 is greater than negative 10. If you know that's the case, and we're dividing these ideas, take negative 7, subtract negative 10. What do you get? You get positive 3, which is my power on my x. So you could go straight from there down to here. Either way works. All right, so the only example we really haven't seen yet is one that involves rational exponents. So let's try a hopefully pretty straightforward one here. Let's take 8, raise that to a power 1/2. Let's break this one down. If you go back to your rules, this would be consistent with the a raised to a power of m over n rule, where denominator represents the index number on the root. Numerator represents the power that we can apply either to our base of a in here or overall to the root. With that understanding in mind, to rewrite this 8 to the 1/2, what I would do is I would take this 2, that's my index number on the root, make this a square root of 8. All that remains is that power of 1, which we can apply on the 8 here or outside, but who really cares? It's 1, right? So the problem becomes square root of 8. It's a square root. You look for perfect squares. We know 4 goes into 8. So you take square root of 4, which of course is 2. You got your root here with the leftover 2 inside. Now let's alter this problem just a little bit. Let's make this 8 raised to a power of negative 1/2. Keep the fractional exponent in there, throw a negative power in as well. We know with that negative power, we're thinking reciprocals. So right now this is technically over 1, right? If I want to get rid of that negative power, I'm going to shift this down to the basement since it's on top. Got 8 to the 1/2 down here. Of course, what does 8 to the 1/2 mean? 8 to the 1/2 means the same thing as what we had back here in number 3. So this would be 1 over the square root of 8. And if we have 1 over the square root of 8, we know that breaks down to 2 root 2. Where for our purposes, you know, we could leave it like that. But ideally, you would get rid of that root. Multiply the top and the bottom by the square root of 2. And in the end, a more simplified answer would be square root of 2 on top over. All right, we've got 2 times the result here when we multiply the 2 roots, which would also be 2. So 2 times 2, we got 4 on the bottom. That'd be a better answer. And if this has not been entertaining enough, let's try this one. This has got some spice to it. 4 raised to a negative 3/2. Think through the process of the previous 2 problems. What would we do first? Okay, reciprocals. This is basically over 1, so we're going to write 1 over 4, the positive 3/2, to create a positive power. Next, what should we do? Okay, we see this denominator of 2. We know that means we got a square root of this base value 4. And the 3 becomes the power either on the 4 or overall. It would make sense to do it overall, right? Because you know what the square root of 4 is. Since we know the square root of 4 is just going to be 2, and you're cubing that result, you've got 1 over 2 cubed, you've got 1/8. All right, now we're going to have some real fun. We're going to take our exponent rules that we know. and we're going to incorporate some of the stuff we reviewed the other day regarding rational expressions, how we add them, how we subtract them. Recall when we add or subtract rational expressions, add or subtract fractions, you got to have common denominators. So when you see a problem of this type, start with the negative exponent. Negative exponent obviously is right here. Since this is a subtraction problem, take note of the expression that has the negative exponent on it and everything that's attached to it. In this case, 11 is attached to that x to the negative 3/4. What I want us to do on a problem of this type is I want us to create a fraction out of this part, right? Because this is all over 1 anyway. If I do that, I'm not playing with the 2x to the 1/4 yet. So I'm leaving that as is. And we're subtracting. Since the negative power is applied to the x, only the x will drop down here. Meaning the 11 stays on top. You've got x to the 3/4 on the bottom. So we got a subtraction problem. We got a fraction involved. We could use our little trick here where if this is over 1, you do the little multiplication here and then you do the cross products, right? Or you could recognize that x to the 3/4 is going to be that common denominator. Let's just multiply x to the 3/4 over here to both the top and the bottom. It's getting ugly, isn't it? All right, if x to the 3/4 is going to be that denominator, we know when we put this together, you got x to the 3/4 down here. How has this numerator over here changed? What does that become? Anybody know?
3. No, 1.
Okay, still going to be 2. But you got like bases, don't you? So if you multiply like bases, what do you do with the exponents? You add them. 3/4 plus 1/4 is, conveniently, 1. So all this goes together, it becomes 2x to the first. And the way these problems are set up, they're kind of rigged that way, so it should come out to be a nice clean power there. In the meantime, you're subtracting 11, right? Because we didn't have to make any adjustments over there. So that's your answer. That's as good as we can do. All right, I figure we could use a little more practice on a similar type of problem. So let's take 1/5 a to the negative 2/3. Let's add 7a to the 1/3 b to the second. Just like we did in the last one, start with the negative power. Got your negative power right here. Obviously, it's a power on the a. So a to the negative 2/3 would be the exponential expression. See what is attached to that expression. When I say attached, multiplied. 1/5 is attached, right? So if we set this up similar to the previous problem, making some adjustments on this 1/5 a to the negative 2/3, what I would do, I know a fraction is going to be created anyway, and I know this negative 2/3 power needs to drop down to the bottom, right? Since this is all multiplied out, let's make this 1 over, because the 1 holds the place up here, 5a to the 2/3. This time we would have a coefficient other than 1 in the denominator just because that 5 was already there. That takes care of the negative exponent stuff. The other stuff just kind of stays as is. Now that we're adding fractions, let's go ahead and find some common denominators. Once again, you could do the little cross product trick, or you could recognize that this is going to be the common denominator. Multiply that over here to numerator and denominator. As we do that, we're going to create one big fraction all over 5a to the 2/3. Considering the numerators we got to put together, you got a 1 right here. That didn't change, did it? But we are adding. All right, let's see what this mess becomes over here. Start with the 7 and the 5, right? Multiply to get 35. If we're doing these correctly, it should work out pretty clean. Notice what happens with the 8 to the 1/3 and the 8 to the 2/3. Yep, 1/3 plus 2/3 becomes 1, so it's 8 to the first. B to the second. That's it. And before we dive into the next one, let's just discuss this scenario. Any thoughts on what this answer is?
Right. Wait, I'd have to give it a set, but your base value is x plus y. Write that out 5 times. And you do it.
There you go. That's the key. You write it out 5 times, right?
Yeah.
So you have x plus y raised to the
Correct.
5th. There you go. These are the same expressions, same quantities, right? Which means they're the same bases. And since they're the same bases, you just add your exponents and keep the base the same. If we can understand that, now I think we can handle this problem. Let's take.
X plus y to the 5th is this, that's the answer.
That's the answer. That's as simplified as it's going to get. Unless we want to expand it out, which I don't think we really want to do. All right, for this one, let's take a minus b raised to the 1/5. Let's subtract 5a times the quantity a minus b raised to the negative 4/5. Hold true to what we've been doing. Locate the negative exponent first. Look, I found it right there. The expression that contains that negative exponent is this a minus b, right? What's attached to it through multiplication? 5a. So what we've done on the previous problems when we've had this kind of situation is we've left the other expression alone, so a minus b to the 1/5. Just kind of leave that as is. But this negative power guy, we create this fraction over here where we bump it down to the basement, right? And really anything else just stays on top. So this 5a right here, there's no negative power. I'm just going to leave this as minus 5a on top over a minus b raised to the now positive power 4/5. Looks like it's time to find a common denominator, right? So if this is over 1, yep, common denominator is going to be this guy. Multiply that a minus b to the 4/5 to numerator and denominator. This is getting messy.
Let's just say b to the first, or a minus b to the first, right?
Yep, and if these problems are rigged the way we think they are, we're going to get one big fraction over a minus b to the 4/5. You've got these common quantities of a minus b as your like bases, so add those exponents. 4/5 plus 1/5 is 1, so conveniently that's a minus b to the first minus the 5a. If we collect some like terms, well, a minus 5a is going to be negative 4a minus b all over a minus b to the 4/5. That's your answer.